Hi all, this is lecture 18. We're talking about 4.8 linear approximation today. So one of the things that we wanted to be able to do and that our calculus can be powerful at is approximating values that we can't get without a calculator. So for example, if you're looking at the square root of 50, that's not a perfect square. So the only way you're going to get that value is if you grab a calculator and take the square root of 50 on there. So let's see if we can use our calculus to determine a way that we can do this without a calculator. So first of all, let's take a look at a picture. So here's the graph of square root of x. Okay, I don't know why it's being a little funky there. Sorry about that. And we want to plug in the number 50. So I'm going to say, okay, let's pretend that 50 is right here. Now, here's the point that I want, okay? But I don't know what the corresponding y value is. So over here, the corresponding y value, we don't know, okay? But we do know that there's a number close to 50 that we know the answer to. So 49 is a perfect square. Whoa, sorry about that. And that one we know corresponds to the number 7. Square root of 49 is 7. Okay, so can we use this to figure out an approximation for the square root of 50? So I want to know what the y value is right there. So what we can do is we can look at the equation of the tangent line at the point that we know. We know the blue point, and we know that we can find the equation of this tangent line. And so at 50 on my equation of the tangent line, it's really close, right? The green dot is very, very close to the black dot, so we can get a good approximation. Okay, so how do we calculate that value? So what we're going to do is we're going to call this the linear approximation. So this is the linear, sorry, my iPad's being a little funky. Might need to be calibrated here. But this is what we're going to call, sorry, L of 50. There we go. The black dot is a y of 50, right? So that's the exact value. And the L of 50 is going to be, L stands for linear approximation. So L is the linear approximation. Okay, so what do? Well, my L of x is this equation for the tangent line. So we just need to find the equation of the tangent line. So we have that the function f of x is the square root of x, which I'm going to write as x to the 1/2. And the point that we're working with is, now I don't know the value for 50. I'm going to project for that one, but I do know the point at 49. So 49, and when we plug in 49 to our function, we get 7. So the y value is 7. Okay, so I have a point and I have a function. So in order to write the equation of the tangent line, I need the derivative of that function at that point. So our derivative, f prime of x, is 1/2 x to the minus 1/2, or 1 over 2 square root of x. And when we plug in our 49 there, so f prime at 49 is 1 over 2 square root of 49, which is 1 over 14. And so now I have my slope, this is my slope, and I have my point. So I have the slope and I have the point. And now we can write the equation of the tangent line. So we know that the equation of the tangent line, and I'm going to use point slope form here. So y minus y1 equals m times x minus x1. And I'm going to use the point as my x1 and y1. And I'm going to use my slope as my m. So that means I'm going to have y minus, the y value is 7. The slope is 1 over 14. And x minus, not 7, but 49. And then let's add that 7 over. So that I get y equals 1 over 14 times x minus 49 plus 7. So that's my equation of the tangent line. So that's the equation of the green line in our picture. And in order to find the approximation for 50, so another name for this is L of x, right? That's my L of x. And so if I want the approximation at 50, then all I have to do is plug in 50. So L of 50 is 1 over 14 times 50 minus 49 plus 7. And 50 minus 49 is just 1, so this is 1/14 plus 7. So that's 7 and 1/14. which is a little bit less than 1/10, right? 1/14 is one smaller than 1/10. So this is going to be about 7.0 something, okay? Because 1/10 would be 7.1. So we've got an approximation. Okay, so we know approximately what the square root of 50 is. It's approximately 7 and 1/14. So can we do this in general so that we can write a formula that we can use every time? The answer is yes. So let's think about what we did here. Okay, so first of all, we had to have a function. So you had a function f of x. Okay, now we weren't given a function, but we created a function. So we had a function of f of x, and we had a value of a point that we knew. So we knew an x value. In this case, it was 49. It was close to 50. And then we used that a to get a point. So we used a, and we plugged in that a to our function to get the corresponding y value. So that would be f of a, right? We plugged in 49 to the square root function. So this is my point from above. And so the last thing I need is the slope. So you have an f of x, and what did we do to get the slope? Well, we're working with the slope of the tangent line because we're writing the equation of the tangent line. So the slope of the tangent line, the m, is equal to the derivative of our function, but at x equals a. So our m is really f prime of a. And that's my slope. And now I have the two pieces that I need. So if we use our point slope form again, you have y minus y1 equals m times x minus x1. And we're going to plug our point in. Our a goes in for y prime. Sorry, our f of a goes in for y1. And our a goes into x1. And then our slope goes in here. Okay, so that means we're going to have y minus, the y value is f of a. The m is your derivative at a. And our x1 is a. And then if you add f prime of a to both sides, sorry, f of a to both sides, you get the following. You get y equals f prime of a times x minus a plus f of a. And this is what we're going to call the linear approximation. So we call it L of x instead of y. So f prime of a, x minus a plus f at a. Okay, and that's where it comes from. And you'll notice on the next page, I stated that for you. Now, notice that what we did up above here, in order to get the value for 50, I then plugged 50 in for my x. So we're going to call that a c. So if we want to estimate for f of c, then we plug c in, and we have the L of c is f prime of a. And instead of x, you're going to plug in your c. So it's c minus a plus f of a. And that's exactly what I stated down here in the definition for linear approximation. Okay, so these are the formulas that you need to move forward. Okay, so let's do another example of each one real quick. So let's estimate the value of the natural log of 1.01. So this is really the second piece there where we're estimating a c. So how do you identify things? Well, first of all, I'm estimating for the value 1.01. So usually what you're going to do is you're going to take that value and call that your c. Okay. And when you take that out and replace it with an x, you get your f of x. So our f of x, when you take out the 1.01, replace it with an x, is the natural log of x. Okay, so that gives me the function and the value I'm trying to estimate for. Now, in order to find the estimate, I need a number that works well in the function, but it's close to my c. And that's what we called the a, right? In the initial example, we used 49. It was close to 50, but it worked well in the function, meaning I could plug it in and get an answer. So what's a number really close to 1.01? Well, 1, right? And it works well in the function because I know that if I plug f of a, plug a into my function, that's ln of 1, which is 0. Okay. Actually, let me put this over here. So my f of a is going to be 0. The last piece that I need to be able to plug everything in is what is the f prime of a. So in order to get that, I need to take my derivative. So we start with the function in terms of x, and we're going to take its derivative first. The derivative of the function is 1 over x Then we plug in our a. So f prime of a, and my a is 1, so this is f prime of 1, is 1 over 1, which is 1. So my f prime of a is 1. And now I can take all of this information to find my L of C, or my L of 1.01. And actually, let me write it down in general first, because that's always good practice. So your L of C is f prime of a times c minus a plus f of a. And I have all 4 of those numbers. So L of 1.01 is the derivative at a, which I have as 1. Your c value, which is 1.01, minus your a value, which is 1, plus your f of a, which is also 1. And so if you do all of that, 1.01 minus 1 is 0.01 times 1 is 0.01. Added to 1, it gives us 1.01. Okay, so actually it's the same exact number. Okay. You can also just find the linear approximation for the function at a value without having a value that you're estimating for. Okay, and in this case, your linear approximation of the function is going to remain a function. Okay, in this case, your f of x is already given, and your a value is already given. So what I need is I need f of a, which just means plug my a, sorry, I jumped ahead of the gun here, cosine of x, plug in the 0, so that's cosine of 0, which is the cosine of 0 is 1. And then we need the f prime at a. You don't need a c value here because you're not approximating for a value. That means I need to take the derivative first. The derivative here is negative sine x. And so when you plug in 0, you get negative sine of 0. And the sine of 0 is 0. And then you have your 3 values that you can use to find your L of x. So L of x is equal to f prime of a times x minus a plus f of a. And that means that my L of x is going to be 0 times x minus 0 plus 1. And that really just turns out to be 1. Okay, your x goes away. So your L of x in this particular case is equal to 1.